problem for how to make our decoders robust day to day. It can actually happen that if you train a neural decoder.
This sounds like a lot of good, fun stuff.
Big problem we have. If you have lag or jitter,
Not quite sure.
the cursor becomes Hi, I'm Avinash, one of the engineers on the ASIC team. We designed the custom neural sensors, which include both analog and digital circuitry, to record and stimulate across 1,024 independent channels. We face challenges across all three major metrics: performance, power, and area. Not only do we have to fit all 1024 channels into a single quarter-sized implant, but we also have to measure spiking activity less than 20 microvolts in amplitude. And today, I'd like to focus on the last challenge I mentioned: power. Power consumption is important to us because we want to give future users a full day of use of their implant without any interruption for charging. Back in 2018, we were sending every sample from every channel off the device for processing, which burned a ton of power. In 2020, we brought spike detection onto the chip. As you may know, neurons transmit information by firing. So simply monitoring for these spikes and only sending these spike events off the implant acts as a very efficient form of compression. And over the past 2 years, we've continued to make optimizations within the ASIC, dropping the total system power consumption down to just 32 milliwatts and doubling battery life. Let's take a look at our on-chip spike detection algorithm, which makes our battery-powered implants possible. We first start by applying a 500 Hz to 5 kHz bandpass filter to remove noise that's out of band. Next, we use an estimate of the noise floor to generate an adaptive threshold per channel. And finally, our spike detector module identifies 3 key points of a spike. Identifying 3 points allows us to detect not just the presence of a spike, but the shape of a spike as well. This can be extremely important for distinguishing between multiple neurons adjacent to a single channel. Today, I'd like to focus on one of the many optimizations that we've made in our latest chip. This one specifically cutting system power by 15%. Note that neurons spike relatively infrequently, which means that our spike detector spends a lot of time searching for the first point of a spike and very little time searching for the other 2 points of a spike that only occur after the threshold is crossed. We can use this characteristic of the input waveform to reduce memory accesses within the chip by 30%. Let's take a look at how that works. Our spike detector is implemented as a single functional unit that's shared across all channels with an SRAM to buffer the state of each channel. As a sample comes in, its channel state is read from SRAM, an incremental spike detection step is run, and then the updated state is written back to SRAM. Since this is happening 20 million times per second across the implant, each of these accesses add up quite quickly. In our latest chip, we split the state into two parts, a hot state and a cold state. The hot state is accessed on every cycle, while the cold state is only accessed once the threshold is crossed, reducing the average access width and saving power. We're also working on a next generation stimulation focused chip with 4,096 channels still within the footprint of our current chips. In addition to increasing the channel count, we're also increasing the drive voltage so we can get better activation per channel. And to support this higher channel count, as well as a broad range of future applications that you'll soon hear about, we're adding an ARM core onto the chip. Chips, we can still put 4 of them together into a single implant for a total of 16,000 channels still within the size of a quarter. As you can see, we've been working very hard to improve the power consumption within the implant, but we've also been working very hard to improve the charging experience of the implant, which Matt will talk about. But first, the robot has just completed inserting all 64 threads, so let's take a look.
It started trending online, and the first year supply sold out in just 6 days.
This thing is amazing. It's made it so much easier.
This is a view
for
of the
me.
insertion site, similar to the one that DJ showed you earlier. But instead of the targeting reticles, if you look closely, you can see that all 64 threads, each carrying 16 electrodes, have been inserted into the brain proxy while avoiding vasculature, and all just within the past 20 minutes. Let's hand it over to Matt now to continue the technical deep dive.
Hi, I'm Matt, head of Brain Interfaces Electrical Engineering. Our fully implantable N1 device depends on a battery for continuous operation. When that battery is running low, charging is accomplished through wireless power transfer. However, unlike many consumer electronic devices, which can simply offer a physical connector, charging a fully implantable device poses several unique challenges. First, the system must operate over a wide charging volume without relying on magnets for perfect alignment. The system must be robust to disturbance and complete quickly so as not to be overly burdensome. However, most important is safety. In contact with brain tissue, the outer surface of the implant must not rise more than 2 degrees C. In pursuit of these goals, our charging system has gone through several engineering iterations. The first, if you watched our pig demo in August of 2020, Gertrude was implanted with a version of the N1 charged with our first generation charger. This device was implemented in a small puck package and later separated into a remote coil and battery base. This charger was challenging to use. However, we learned a lot through its implementation. Our current production charger, which charges our current generation of implants, is implemented in an aluminum battery base, which also includes the drive circuitry. A remote coil, 4 times the size of our original device, also disconnectable. This remote coil has increased switching frequency, driving improved coil coupling. This charger is in use today, including several applications within our engineering and animal test facilities. I'd like to show you one of these applications here with a device we call our simple charger. And the coil has been embedded into the habitat. With the addition of one new outer control loop plus a banana smoothie pump, the troop has been trained to charge themselves. So let's see how Pager charges his implant. On the right, we're streaming real-time diagnostics from Pager's N1. When he climbs up and sits below the coil, you can see the charger automatically detect his presence and transition from searching to charging. We see the regulated power output on a scale of 0 to 1 and the current driven into his battery. I mentioned earlier that we improved the coil coupling. However, the high quality factor coils exhibit good charging performance over relatively larger distances, but as they're brought closer to the implant, what you see is a peak splitting effect, where the best, highest efficiency power transfer is pushed up into higher frequencies outside of the ISM band required for compliance with regulated radiated emissions. In our next generation charger, we address this problem by the introduction of dynamic tuning, shown on the right. This allows us to, in real time, adjust the resonant frequency of the transmit and receive coils so that we can change their properties just ahead of degraded performance. The electrical engineering team is currently engaged in developing a third generation charger. Notable improvements include bidirectional near-field communication. This has allowed us to reduce the control latency and improve the thermal regulation. Improved thermal regulation results in faster charge times. And now, Julian will tell us about how we test the N1.
Thank you very much, Matt. My name is Julian, and I lead the embedded software group on the Brain Interfaces team. So when we started building implants, we had a small manufacturing line, and to collect data from an implant, you would manually walk over with your laptop, you would connect, and collect the data of interest. But our goal is to make an ultra-safe and ultra-reliable implant. And so to do this, we scaled up the manufacturing line, our testing throughput, and data collection capabilities. So firstly, we added a large suite of acceptance tests to the manufacturing line. These test the functionality of each component and the final assembly. Implants coming off the line are then subjected to benchtop testing, accelerated lifetime, and animal models. We then collect data from these implants round the clock. This data is processed by a series of cloud workers and displayed in an aggregate manner. And then finally, all of this information feeds back into our design process and empowers our engineers to answer any question about any implant at any time. I'm now going to walk you through different parts of this infrastructure, starting off with firmware testing. So the implant contains a small microprocessor running firmware to manage a whole bunch of its operations. And before we release a firmware update, we want to rigorously test it with both unit and hardware-in-the-loop tests, also known as hill tests. So to do a hill test, what you do is you instrument the battery, you instrument the power rails, the microprocessor, and then we connect to each device with a Bluetooth client. And then we walk the devices through various scenarios to test things